And welcome to my talk about computer-assisted existence proofs for Navier-Stokes equations on an unbounded strip with obstacle. Let me first of all mention that this is joint work together with my supervisor, Michael Plum, who will give a second talk to this topic afterwards. And let me start with some introduction about the equation and the domain we're considering. So we consider the incompressible stationary Navier-Stokes equations on a unbounded strip domain omega, which is defined as the strip R times 0, 1, perturbed by some compact obstacle D. And then we consider the stationary incompressible Navier-Stokes equations, where we have the velocity function V, the pressure Q, and we have the Reynolds number here, which is denoted in the literature by RE. And we use this notation in the further course. And then we are interested in solutions which consist of some background flow, and we use the Poiseuille flow, capital U, as background flow. So we look for solutions of the form V is equal to U plus some function U bar, where U bar tends to 0 as X goes to plus or minus infinity, which is somehow natural since we have a compact obstacle. The influence of this obstacle only is in some finite part, and so at plus or minus infinity we expect to have the background flow u here, and with the pressure we use the transformation with the corresponding pressure. Then inserting this in our Navier-Stokes equations, we end up with this, and then we see that U is actually divergence-free and solves the stationary incompressible Navier-Stokes equations on the strip. So these terms here vanish, and we end up with this system here. And let's now have a closer look at the boundary condition for our new function U bar. Then we see that our Poiseuille flow is equal to 0 on the boundaries of the strip, but non-zero at this part of the boundary of the obstacle. So we get somehow a splitted boundary condition for our new function U bar, which is given like this. So U bar is equal to 0 on the boundary of the strip, so on these straight lines here, and it's equal to minus the Poiseuille flow on the boundary of the obstacle intersected with our boundary of the domain. And this splitted boundary condition is somehow nasty for the analysis and also for the numerics. So we want to have a homogeneous Dirichlet boundary condition here. And so we introduce a second transformation with some function V. So U bar is equal to our new function U minus some function V, which is divergence-free and equal to 0 on the boundary of the strip, and equal to our Poiseuille flow at the boundary of the obstacle intersected with the boundary of omega. And we get the same relation here for our new function U. It should be tending to 0 as X goes to plus or minus infinity. Let me mention at this stage here that we can construct this function V explicitly such that the support of V is compact in the closure of our domain omega. Then inserting this in our equations, we use the abbreviation gamma here and end up with this system here. And then we can use that the V is actually divergence-free, so this term vanishes here. V is constructed such that we have now homogeneous Dirichlet boundary conditions for our new function U. And these terms here, which are written in blue, they are independent of our new function U, so we can put them on the right-hand side, and we will denote them by G in the further course. And so we end up with the transformed Navier-Stokes equation given like this, which will be considered in the further course. So we have this homogeneous Dirichlet boundary condition here and the divergence-free condition for U. And we look for weak solutions in this divergence-free subspace of H10. So this second equation here is given by our space itself, and also the boundary condition are modeled here in the space. And so we look for weak solutions here, and we can endow this space H with the inner product given like this here, and then we get a real Hilbert space H. And let me just give a short remark on this parameter sigma. We can choose this parameter sigma arbitrary, so but non-negative, and this will be chosen later. And let me just give a short remarks. We can also choose sigma equal to 0 since we have Poincaré's inequality for our domain omega, since we're bounded in y direction. And then this inner product introduces an isometric isomorphism, which will be denoted by phi in the further course. And now let me just give some details about the for the computer-assisted proof. So when we need a zero finding formulation of our problem, so we define the operator f by the weak formulation of our problem. And let me mention at this stage here that by using the divergence-free test functions, we are in a position to eliminate the pressure from our equation. So we only have an equation for our velocity field u. And then we see that u solves our transformed Navier-Stokes equations in a weak sense, if and only if it's a 0 to our operator f. And then we compute an approximate solution of our transformed Navier-Stokes equation in H, which is always the case in computer-assisted proofs. And then we can form or define the linearization of f at this approximate solution omega, which will be noted by L in the further course and is given by this formula here. Let me next give some details about the assumptions needed for our existence and enclosure theorem. So we need constants delta and k positive, satisfying these assumptions A1 and A2. So first of all, delta is a bound for the defect or the residual of our approximate solution omega. And what we can expect is if our approximate solution is computed with high accuracy, we expect that delta is also small. And then k is a norm bound for the inverse operator of L. So we have assumed that k is at hand, satisfying this inequality here. And from this inequality, first we get that L is injective, and we also want or need for the proof of our theorem that L is surjective. And so we first of all realize that by this inequality we get that the range of phi inverse L is closed. Now we want to prove that the range is also dense in H, and in the former applications of the computer-assisted techniques, this denseness of this range comes from symmetry assumptions on L, but we do not have the symmetry here in our Navier-Stokes case, so we need an additional assumption to guarantee that the denseness of this range here. So we assume furthermore that we have a constant k star positive in hand, such that this adjoint inequality holds true for this k star. And then from this inequality, we obtain that this operator here is actually injective. And by this equality here, we get the denseness of the range, which together with the closeness yields that L is surjective. And let me just mention that phi here is an isometry, so we get this surjectivity of L. And let me just mention that the computation of this constants k and k star will be discussed in the second talk by Michael Plum, who will give this talk afterwards. And now with this constants here in hand, we are in a position to show or prove the main existence and enclosure theorem, which is formulated like this. So we assume that we have an approximate solution omega in hand, and also this constants delta k and k star, non-negative or positive, such that they satisfy these assumptions A1 to A3. And then we can check by verified computations on the computer if this inequality holds true. And if this is the case, then there exists a locally unique solution of our transformed Navier-Stokes equation, or 0 of our operator f. And this solution also satisfies this enclosure estimate here. And let me give a short remark on this first inequality here. So as I said before, delta is somehow characterizes the accuracy of our approximate solution. And so if we assume that our approximate solution is computed with high accuracy, we expect that delta is small, and then we expect that this inequality can be satisfied here. Moreover, this constant k star here, which is satisfies this assumption A3, does not appear in our error estimate here. So this constant k star is actually only needed for the fact, or to show that our linearization is surjective, and it's not needed for the error bound here. And when we have proven such a solution U star of our transformed Navier-Stokes equation, we can use the transformation from the beginning to retransform the solution. So we're adding this factor of this gamma here, this function gamma, and obtain a solution V star of our original Navier-Stokes equation, which I presented on the first slide. And in the further course, I would like to give some details about the computation of the approximate solution and the computation of the defect bound delta. And as I said before, the computation of k and k star will be discussed in the second talk by Michael Plum. So let's start with the approximate solution omega. And let me recall that we need an approximate solution omega, which is in our space H. And therefore, we require an exactly divergence-free approximate solution. And since our domain omega is unbounded, we restrict ourselves to bounded computational domain omega 0 and look for solutions which are of this form here. So we actually compute an approximate solution omega 0 in this divergence-free subspace of H10 defined on this computational bounded domain omega 0, and then extend this by 0 to obtain our approximate solution omega. And let me just give two short remarks here. First, when we extend this by 0, we get a function in H10 of the entire domain omega. And we expect that this approximate solution is not worse, since we have the assumption that our solution U tends to 0 as x goes to plus or minus infinity. So we do not expect to have a great residual here caused by this cutting off by 0. And furthermore, this omega here is divergence-free, since we have an omega 0 computed as a divergence-free function, and we extend this by 0, which is also divergence-free. So omega is actually a function in H. And we are left with the computation of this function omega 0, and therefore we use divergence-free finite elements based on Aguirre's elements to compute this omega 0 here. And then as a second step, we compute the defect bound delta. So we require a delta positive such that this bounds the defect of our approximate solution omega. And here I just wrote down the operator f. And what we actually wanted to use is Cauchy-Schwarz inequality here. But since omega is a finite element solution extended by 0, we do not have regularity here to use integration by parts. Therefore, we compute a function rho in HDiff, which means that we have a row-wise divergence in L2 for this row. And then we insert this into our equation. So we have this term rho here and this additional difference here. And then we can, since we have this row-wise divergence here of rho, we can use integration by parts and obtain here this minus divergence. And now we can apply Cauchy-Schwarz inequality on both terms and end up with this inequality here for the residual measured in the dual norm, which can be estimated by this terms here. And this will be our constant delta. Let me just give a short remark on the computation of this function rho here. We somehow minimize our delta, or we want to have a small delta here, since this delta somehow measures our accuracy of our approximate solution. So we're interested in a small delta, and therefore we minimize a suitable functional here to compute such a row, and then we can define this function delta. Let me just give a short remark on the computation of this L2 norms. These norms actually have to be computed using verified quadrature formulas. And in our cases, we do not need to use remainder term bounds, since we can compute these integrals with an verified quadrature formula of sufficient order to enclose the value of the integrals here by numerical or interval arithmetic means. And as I already said, this computation of the norm bounds k and k star will be discussed in the next talk. So we assume for the moment that we have computed such constants delta k and k star as well, and then we can check our assumption in our main theorem. And so I want to present some results which we achieved. So in these cases, we have computed delta and k, and checked the inequality in our existence and enclosure theorem. And this proves the existence of a solution of our transformed Navier-Stokes equation, which we have this error bound here in this case here. And let me just recall that we can retransform the solution by adding this function gamma here. And then you see here the approximate solution gamma plus omega from our original Navier-Stokes equation. And here you see the streamlines, and also on this picture you see the streamlines of this approximate solution to our original Navier-Stokes equation. And so we expect, since these error terms here are small, that the original solution is really close to this solutions plotted here, to this approximate solutions. And let me just give a short remark on this second plots here on the Euclidean norm of this approximate solution. So we see here that we actually have the background flow or Poiseuille flow, and the part of the obstacle where the our strip is getting thinner, and we have here a higher velocity, which somehow fits in our physical intuition. So here the velocity is larger. And let me just give two other examples where we successfully applied our techniques here. So we have this domain where the obstacle is actually detached from the boundary. So we actually have here a domain which is not simply connected anymore, but our techniques also apply to domains like this, since we do not require a stream function formulation of the problem. We can also apply our techniques to non-symmetric obstacles, which are presented in this picture here. And let me just give a short remark on the colors in the background here of this plots here. So in the background, you see actually the plot of the pressure, which is also part of the original Navier-Stokes equations. And what we actually can prove, or if we have proved the existence of a solution U star, or this transformed V star, then we can reconstruct the pressure. So let me short recall the transformed Navier-Stokes equation. And so we assume that we have a solution U star of our transformed Navier-Stokes equations, which is given by our existence and enclosure theorem. And then we can prove the existence of a corresponding pressure P star in L2 log of the closure of omega, such that this weak formulation here is satisfied for all phi in H10 with compact support. And this theorem can actually be proven by purely analytical means. And then we have that U star, P star is a weak solution of our original transform of our transformed Navier-Stokes equation. And then by retransforming this with gamma and p, we get a solution, weak solution of our original Navier-Stokes equation. And since we are in the setting of computers, these proofs are interested in some error estimates. We also give an error estimate for the pressure. So we assume that we have computed some approximate solution to the pressure, and we want to give an error bound of this term here in the h-1 norm. And therefore, we first of all use that p star, which is computed or proven analytically. This satisfies this equality here in a weak sense. And what we actually want, we want to insert this into our norm here. But we have this u star here, which is our solution of the transformed Navier-Stokes equation. And we do not have this u star in hand here, but we have our approximate solution used in the existence theorem. And so we somehow use this approximate solution to estimate this norm here by the following three terms. So we have here a term where we actually see that it's quite similar to the computation of delta. To estimate this term, we can use the same techniques as for the computation of delta. Then we have this term here from h-1 norm, and we have this additional term here. And then you see that we can compute this, as I said before, similar to delta. And here we always have this term, this difference of u star and omega. And then we can estimate this here and this here by the norm of omega minus u star in h. And this is, therefore, we can use our error bound, which is given by our existence and enclosure theorem. So this term here can directly be estimated by the difference of omega minus u star in h. And here we get this term here where C4 is actually, again, the Sobolev embedding constant. And here we have these terms, the infinity norms. And let me just give a short remark on the computation of this infinity norms, which has to be done by verified computations. And therefore, we since all these terms are polynomial, we use representation in Bernstein polynomials to enclose the range of these functions here, and therefore we get an verified estimate for the norms here, which are required for the computation of this defect bound. And as I said before, for this term, we know an error bound with, provided by our existence and enclosure theorem. And that's all I wanted to say for today. So thank you for your attention.